拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。能够像我一样飞越最高山岗。
在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待，技术革新浪潮汹涌而至。对其高性能的需求、无限小型化的追求，成为行业发展的必然趋势。多层陶瓷电容器、电感器、高可靠性元器件、太阳诱电支撑其全流程的先进技术，提供给用户全方位的服务。为了科技的发展，我们一代代太阳诱电人肩负使命，激情拼搏，以极致的匠心独运呈现出史诗级作品，研发历程感动了无数电子工程师。太阳诱电将深深吸引全世界的目光。
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心 没有什么可以阻挡心中无限的力量。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。能够像我一样飞越最高山
岗。在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待，技术革新浪潮汹涌而至。对其高性能的需求、无限小型化的追求，成为行业发展的必然趋势。多层陶瓷电容器、电感器、高可靠性元器件、太阳诱电支撑其全流程的先进技术，提供给用户全方位的服务。为了科技的发展，我们一代代太阳诱电人肩负使命，激情拼搏，以极致的匠心独运呈现出史诗级作品，研发历程感动了无数电子工程师。太阳诱电将深深吸引全世界的目光。
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can，没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。
Hello, everyone. Welcome to our this week youth talks. Today we'll have 5 attendants. So my name is Yu Song from City University of Hong Kong. So we also have Professor Fan from University of New South Wales as a speaker, and also Professor Hao Tianchen from University of Glasgow as another speaker. And we are also very happy to invite Professor Yanfang Guan from Henan University of Technology, and also Professor Haixia Zhang from Peking University as the panelist for the later discussion. So today our topic is about the stretchable electronics and origami metamaterials. So our first speaker is Professor Fan. So let me give a very brief introduction about Professor Fan. So today his title is about silicon carbide nanomembranes for sensing applications. He got his bachelor and master degree from the University of Tokyo, and then the PhD degree from Griffith University. He is currently an associate professor and the ARC Future Fellow at the School of Mechanical and Manufacturing University, the University of New South Wales. And he also his mainly research focused on the semiconductor devices and application, including the MEMS, NEMS, integrated sensors, flexible electronics, and the three-dimensional microarchitecture. He also was a visiting scholar at AIST Japan and also Stanford University and Northwestern University. He published over 140 journal papers like Nature Communications, Science Advances, PNAS, Science Robotics, and some other prestigious journals. He also got some awarded like Springer Outstanding Thesis and the Australian Nanotechnology Network Fellowship. So let's welcome Professor Fan for his talk. So I'll stop sharing, and Professor Tan, the stage is yours.
Right. Thank you very much, Professor Yu, for your kind introduction, and I will start sharing my screen now.
Yeah, we can see.
All right. Can you see my screen?
Yeah, we can see your screen. You can share.
All right. First of all, thanks for having me here today. Many thanks to Professor Alex Chang for your
Now it's at the display setting. Can you change to the full screen?
full screen. Is it okay now?
No, not yet. So maybe you can click the upper the display setting, that one.
Let's see.
I guess you can stop sharing first. You yeah, use share the screen. You can use the slides to full screen slides first, and then share the screen to select that window. That will be better.
Okay, got it. Actually, we use Zoom at my university, and we use Teams at my university, so not very familiar with Zoom.
Yeah, sometimes.
How about now?
Let me check. Wait a moment. Yeah, now it works. Yeah, go. Yeah, you can go ahead. Thank you.
Let me check. Is that okay?
Yeah, it's good now. Yeah.
All right, cool. So many thanks, Professor Yu, for your kind introduction, and also Professor Alex Chang for your invitation, and thanks other member for being here today. So my name is Vance. I'm an associate professor at the University of New South Wales, Sydney in Australia. Before I start my talk, I would like to give a very brief introduction about my university. So University of New South Wales located near the center of of Sydney. And you know that Sydney is the largest city in Australia and one of the largest technology and financial hub in the southern hemisphere. And it has beautiful landscape and very rich culture. And Australia also the home of several innovation like Wi-Fi, ultrasounds, and bionic ears was all invented in Australia. And 90% of the solar panel in the world are actually made from our university invention from Professor Martin Green. Globally, we have quite good ranking based on the QS ranking. Our university ranked number 19, and our faculty of engineering all the way ranked number 1 in engineering and technology in Australia for many years. And students from our university as Australian most employable student. We have at school, chemical, mechanical, electrical engineering, and so on. We have quite beautiful campus. And here the map, the Google map of our university. It is about 7 kilometers from the Opera House. I hope that many of us know the Opera House, a landmark, a very famous landmark in Sydney and Australia. And it's about the 2 kilometers from the beach. So it's very good location for studying, working, and enjoying life. And my research lab working on intelligent microsystems for a range of application, mainly for application here and a bit overlapping as well. We work on silicon-based micro electromechanical system or MEMS for wearable and robotics application. We also develop a 3D architecture for organ-on-chip technology, sensor for extreme environmental monitoring, and silicon carbide electronics for long-term bioimplants. So today's my talk will mainly cover this area. And so here's some picture of my recent trip to China. So I was quite fortunate to be able to arrange a trip to China last month. Visited a few universities and also met a number of friends, including Professor Alex Chang at Peking University. And the trip, it is almost 10 years from my previous trip to China. And I was really amazed by how well the country has developed over the last 10 years, like very modern and well developed architecture and infrastructure. And you also keep very traditional landscape like this, which is really amazing. And so there are many things that I was very impressed when I visited China last time. And one of that thing was there's a lot of electrical or EV cars in China. It's like I saw many BYD, Havel, and so on in China. And later on, I also visited Shandong University, one of my former college, now working as a professor at Shandong University. And they're actually a key research institute in China for wide bandgap semiconductor. I think the main focus material at Shandong University is silicon carbide. They have several $100 million project there. It's amazing that they have about 10 CVD chamber running 24/7 to grow silicon carbide material. And later on, they also build silicon carbide Schottky diodes and MOSFET device for power electronics. And the reason they receive a lot of funding and investment and also highly focused on silicon carbide technology is because nowadays several EVs actually use silicon carbide power devices such as BYD, HP, NIO, and Tesla, and even Hyundai also using silicon carbide power devices. The reason that people use silicon carbide instead of silicon is because it have a typically larger breakdown voltage, about 10 times higher than that of silicon. So it can operate at much higher voltage, above 1000 volt. It also reduce the size of inductance and capacitance so that the power module can be very small by using silicon carbide. And it also enhances its efficiency compared to silicon-based power devices. So that's why many EV company in transportation, like in Japan, Panasonic also shipping into silicon carbide power devices. The market of silicon carbide power devices is quite promising, expected to be around $8.5 billion in 2030. So it's really exciting research area. And not only having a large breakdown voltage for hyperelectronic, its energy bandgap is also double or triple silicon, making the material more stable, electrically more stable at high temperature. It also has higher Young modulus so that it can offer larger resonant frequency. And it has excellent chemical inertness and much higher melting point compared to silicon. So all of the material makes silicon carbide an excellent candidate for sensor and electronic in extreme environment where silicon cannot be used. So why we have to care about the extreme environment where silicon cannot be used? Because in many industrial sectors, we have to deal with extreme conditions, like in space and deep sea exploration, the pressure level can be very high. If you remember, an incident happened a few years ago when a submersible imploded when it go deep into the sea because of high pressure level. And in Australia, we have energy industry is one of the most important sector, like mining and energy. So we have about 37,000 kilometer pipeline system, and the condition inside the pipe is highly corrosive because of the gas flow, the continuous gas flows. And for that engine and so on, we also need to deal with extreme environment because of high temperature. It costs around $1 million US dollar to disassemble that engine to annually inspect it. So if we have devices that can be embedded directly inside the engine that have us to continuously monitor the condition of the engine, it can save a lot of money. And any error that happen in these extreme conditions can lead to catastrophic failure. And one of those is the San Bruno pipeline explosion in California in 2010. People can smell the gas leakage in the area, but there was no gas sensor that can detect the leaking location. And later on, when it catch heat, it exploded and killed 8 people and pollute the environment. So there's the need to develop a sensor that can monitor the condition of pipe, detect the leakage or cracked area. Another also quite well known in the field of extreme environment is space exploration. So in the late 1980, early of 1990, there was a competition between the US and Soviet Union in launching this kind of devices, a robot or rockets, to Venus. The reason is Venus is expected to have a very similar climate condition like the Earth about 200 million years ago. And NASA was quite interested in what turned Venus from almost livable planet like the Earth into a very extreme planet like now, like the temperature at 450 degrees C. It have acid rain and very high pressure level. And at that time, after invest $1 billion, the Soviet Union finally had this kind of devices or robot launch onto the surface of the Venus. But they use silicon material and sensor, which was carefully packaged inside a titanium container. But the device only lasts for 127 minutes. It only able to send a few pictures back to the Earth's base observation sensor. And then after that, it completely did function because the device using silicon couldn't withstand extreme environment. So the example highlighted the need to develop material and devices that can operate under extreme environment where conventional silicon can no longer be used. And with its superior physical and chemical property, and together with the availability of silicon carbide material in the market, it is a good candidate for this research direction. However, similar to the power silicon carbide devices, the materials still have a few challenge for a sensing application, and one of those is the material cost. This data is a bit old now, but the price of silicon carbide 4-inch wafer still in the range of few thousand US dollar per 4-inch wafer, which is approximately maybe 2 orders of magnitude more expensive than a silicon wafer. Another problem is it has chemical inertness property, which is really good for highly corrosive condition, but it also makes it really challenging to pattern microstructure of silicon carbide if we start from the bulk wafer. So our solution to address the problem to make silicon carbide more suitable for micro electromechanical system or MEMS application is to grow thin film silicon carbide on low-cost silicon so that we can significantly reduce the cost. And with that platform, we can utilize the standard silicon MEMS fabrication process to make silicon carbide microstructures. So we have developed the low-pressure chemical vapor deposition process, LPCVD, to grow silicon carbide on large-scale silicon wafer with wafer size up to 300 millimeter. And we can grow multiple wafer in a single process in our chamber, up to 50 wafers. So we can expect to reduce the cost of the wafer down to the few $100, significantly lower than that of the bulk wafer. And we can also control the thickness of the silicon carbide by controlling the number of growing cycle. So we can have silicon carbide thin film with thickness of few 10 nanometer up to a few 100 nanometer, depending on the applications, and highly suitable for flexible electronics, which I will present later on. And we also have silicon carbide, have developed silicon carbide dry etching process with etching rate about 100 nanometer per minute, which is very reasonable for silicon carbide nanothin film. For example, if you start with a few hundred nanometer, like 200 nanometer silicon carbide film, you can make microstructure within a few minutes. And with the platform silicon carbide on silicon, you can also utilize standard e-beam lithography or focused ion beam to make nanostructures like nanowires. And because silicon carbide have very good chemical inertness, so you can selectively remove the silicon substrate without attacking the silicon carbide material. You can selectively remove silicon using KOH, HNA, or TMAH, and then at full scale wafer, so that you can have freestanding like 200 nanometers in carbide membrane like this picture. And you can also make nanowire, nano originator using e-beam lithography. And because we aim to silicon carbide for application in extreme environment like high temperature and high oxidation, so the first step that we investigated is the tolerance of silicon carbide to oxidation at like nearly 1,000 degrees C. The material will grow at 1,200 degrees C, so we test near that temperature. And we use the calorimetric to observe the change in the property of the material. So when we test around 950 degrees C, we saw almost no color change in silicon carbide on the silicon substrate. But above that, we found that silicon carbide start to oxidize, which also matched really well with the optical profile. The optical profile showed that silicon carbide was relatively stable if we oxidize below 1,000 degrees C. At above 1,000 degrees C, you see significant drip in the optical reflection. And we also confirmed that with electrical property, we oxidize the material at 1,000 degrees C for an hour. And after that, we measure the electrical conductivity. It retained the excellent electrical conductivity after the oxidation test, meaning you can use the material around like 1,000 or 950 degrees C. And with this property, we found that like you cannot oxidize silicon carbide at 950 degrees C, meaning you can selectively oxidize silicon underneath of silicon carbide, because you can easily oxidize silicon using either dry oxidation or wet oxidation. And that's a property that we utilize to form silicon carbide on insulator very similar to silicon on insulator, and we call it SiCoI, silicon carbide on insulator, SiCoI. So the method that we form silicon carbide on insulator is we grow silicon carbide. We start with silicon wafer, we grow silicon carbide on silicon, and then we use e-beam lithography to make nanowire, silicon carbide nanowire in green color here, and expose silicon a bit. And after that, you can oxidize at 900 or 950 degrees C, where silicon will be oxidized, and silicon carbide is not attacked. And by doing so, you will be able to selectively oxidize the silicon layer underneath and have silicon carbide on oxide layer. And here's some SEM image that demonstrate the concept to form SiCoI. Right, with the platform silicon carbide on silicon, we have investigated a number of applications from mechanical sensor for extreme environment, high Q factor and high resonance frequency resonator. Also, it is a good platform to grow gallium nitride because they have very good lattice constant matching. And you can use that for temperature sensing, and it has excellent biocompatibility, so it is suitable for microfluidic and bio application. And we have trained a number of students, postdoc, and academics from this research direction. And a few examples, I don't go into the details here, that we can utilize silicon carbide for sensing application is the piezoelectric effect. It's very similar to the case of silicon. Like when you apply strain into the material, it will deform the crystal structure. It will change the lattice constant and will change the energy bandgap. So when the energy bandgap change, the electron will redistribute following the Boltzmann distribution. Like electron will feel lower energy level, and you have the redistribution of electron, and it also change the mobility. And at the end, it change the conductivity of the material. And because we grow silicon carbide on silicon, so we expect the material have similar crystal orientation. For instance, if you grow silicon carbide on 100 silicon, you have 100 silicon carbide cubic. If you grow on 111 silicon, you end up with 111 cubic silicon carbide. And we know that the piezoelectric effect in silicon is orientation dependent, so we expect the same phenomenon in silicon carbide. And we build this kind of piezoelectric coefficient tensor to investigate the orientation dependent silicon carbide for mechanical sensing. And interestingly, we found that silicon carbide exhibits orientation dependent property. For example, for p-type silicon carbide doped using aluminum, we have the piezoelectric effect will be maximum along the 010 or 100 direction. And on the other hand, for anti-silicon carbide doped with nitrogen, we will have the maximum sensitivity along 110 orientation, meaning based on these piezoelectric coefficient, we can decide which crystal orientation we offer the maximum sensitivity, and which orientation can be used for temperature compensation circuit. And we also develop some smart mechanical structure to further enhance the sensitivity of device using silicon carbide piezoelectric effect. So the gauge factor of silicon carbide p-type at room temperature is about 30, about 4 times lower than that of silicon. And to enhance the sensitivity, we can use this kind of dot bond structure. So the dot bond structure is very common structure used in material engineering. So when you test the tensile strength of a material, you use this structure, and then you use the pulling test. And then when under the pulling test, the crack always happen at the narrow area because of the stress concentration. So using the same concept, we make like nanowire along with nanoframe on a freestanding membrane like this. It forms a dot bond structure. So when the membrane deflects, more strain will be concentrated on the narrow area, which are the nanowire here. And by using this structure, we can amplify strain induced into the nanowire and then enhance the output voltage because of the piezoelectric effect. And we demonstrate the concept using the focus ion beam to make nanowire here. And using small nanowire, we can enhance the sensitivity by around 5 times compared to the bulk silicon carbide piezoresistor. And we aim the material for extreme environment, especially high temperature. Typically, silicon is used below 150 degrees C. So here in the test, we test above 350 degrees C and 300 degrees C. And the gas factor of silicon carbide was relatively stable. It dropped a bit from like nearly 30 down to around 26 at 300 C. The reason that we couldn't test at much higher temperature was because of the instability between the metal and semiconductor interface. That's something we need to further investigate in the future. And we also demonstrate pressure sensor using laser cutter. You can remove the substrate and form very thin silicon carbide nanomembrane that you can use for pressure sensor under corrosive condition. And silicon carbide is the key material for power electronics. So we also interested in integrating NEMS and microfluidic technology for silicon carbide power device. One of the ideas that we developed in our ARC industrial linkage project is to integrate microfluidic with silicon carbide power devices so that we can reduce the heat from the device and maintain its high performance for power converting application. And we use two-phase flow liquids, ferromagnetic liquids, circulating above silicon carbide heater to remove the heat. So we can reduce the heat around like from 15 degrees C down to nearly 90 degrees C using the liquid flow. So in this project, initially we used silicon carbide on silicon platform at a proof of concept, but we found that when we increased the temperature, there was a significant current leakage from silicon carbide to silicon because the junction between silicon carbide and silicon cannot tolerate very high temperature. So that's the need to develop silicon carbide on insulator. And as I mentioned in the previous slide, we can locally oxidize the silicon substrate to form silicon carbide on insulator, but it requires focused ion beam or e-beam lithography, and the yield is not very high. We want to have a more scalable process that can transfer the whole silicon carbide wafer from silicon onto insulator. And one of that process was to use ionic bonding to bond silicon carbide on silicon wafer to a glass substrate. And then after you remove the silicon substrate, you will have silicon carbide completely on insulator like this, a transparent thick silicon carbide on glass wafer. And we also collaborate with the University of Tokyo to explore its bonding strengths. And under the pooling test, we found that the crack always happened within the glass material, but not at the interface, meaning the bonding at the interface even stronger than the bulk glass substrate. And before we optimize the bonding condition like pressure, surface treatment to obtain a good bonding between silicon carbide and glass, we experienced a lot of failure. And the way that that help us to quickly test the bonding strength between silicon carbide and glass wafer was this use a Scotch tape, very similar to the way that people used to make graphene many years ago. So you use Scotch tape, you stick to silicon carbide, you peel it out. So if silicon carbide stick on Scotch tape, means your bonding condition is not really good. You need to optimize that. And we also experienced that at the beginning. Later on, we optimize the process, and then we have very good, strong bonding condition. However, when we use the Scotch tape and we peel it off from the glass substrate, we found it really interesting to have silicon carbide on polymer, which means it can be flexible. And because when people talk about silicon carbide, they always think of a brittle material, and no one tried to make silicon carbide on flexible substrate before. So we were quite excited to have this the platform, even if it was a failure for the project. However, when the next question comes to us is who care, like why we need to have silicon carbide on polymer, why we need to have flexible silicon carbide electronics. And because we already have silicon, can work very well on polyamide. However, silicon is mainly used for bioresorbable electronic or for bioresorbable implants application, which Professor John Roger Group has extensively worked for several years. But if we look at the implanted electronics, it is very similar to a conventional implants. We always need two systems together. The first one is dissolvable implants, meaning once the patient heals, the device would disappear, like the screw here. When the bone regrow, it should disappear. And for post-surgery, like post-surgery monitoring, if you just want to temporarily monitor the condition of the patient after a few months, then you need to have a biodegradable device that can measure a few months, and then after that it can just dissolve by itself. So we have quite a good library of material that can meet this condition. Like we have PLGA, silicon, magnesium, and tungsten, all can dissolve. But however, we also need long-term implant application, especially if we have a knee joint like this. When we implant, we want the joint to stay there over the lifetime of the patient without replacing. And similarly, for chronic disease, we also want to have implants device stay over the lifetime of the patient without extra surgery for removal and replacement. We have quite good material for the substrate and metal interconnect like titanium or platinum, but we don't have very good bio-barrier and bio-interface that can protect underlying electronics. The moment when I show silicon carbide, and I also know that it's really hard to wet etch silicon carbide. I think the candidate is the material have great opportunity in the field of long-term flexible implants. So we investigate the methods that can help us to controllably transfer silicon carbide from silicon onto a polymer substrate, not just randomly pick up using the Scott tip. And before that, we go back to fundamental mechanical concept, how to make silicon carbide flexible because it's a brittle material. So the concept really simple. So if you can thin down silicon carbide from a few hundred micrometer to a single layer, like this image, like if you have a thick book, if you can thin down to a single layer paper, it will become flexible. So the idea is if we grow very thin silicon carbide on silicon, a few hundred micrometer thick silicon, and get rid of silicon layer and transfer silicon carbide onto a polyimide layer, then the polyimide layer will actually dominate the bending stiffness of the bilayer of silicon carbide and polyimide. And in that case, we will have flexible devices. And to controllably transfer silicon carbide from silicon onto a polymer substrate, we engineer the process that has been developed for silicon and apply that to silicon carbide. But one of the major differences is silicon carbide directly grow on silicon, so it doesn't have any superficial layer. So the way we transfer that was to make silicon carbide freestanding membrane on silicon using KOS like this. And then you can actually do lithography directly on silicon carbide and you dry etching to make silicon carbide microstructure and freestanding. And you can use PMS stamp to stamp this structure, to pick this structure from silicon substrate onto PMS and then further transfer it to polyimide. And here's some photo of the different structure that we successfully transfer onto PMS and then polyimide. So under the simulation, we also always found that the crack concentrate at the anchor of the microstructure able to beautifully detect the microstructure from silicon membrane and onto PMS. And later on, we developed another fabrication technique that allows us to transfer random structure, not only through stamping, but by direct lithography on both sides of silicon carbide. The membrane is relatively strong. It will allow you to spin coat photoresist on both sides of the membrane. You can have metal on one side and polymer on the other side, and then you can detect the whole structure from the silicon substrate, like some silicon carbide on polymer flower like this. It can easily follow the curvilinear surface of a liquid droplet, meaning it is highly flexible. And here's another picture of highly density silicon carbide electrode array that you can form on a silicon on a polymer substrate. And then for flexible implant, we also investigate mechanical property. So we use the bending test to confirm that the electrical property of the material is very stable after several stretching bending cycle. And for long-term implant, we want to see how long the material can withstand in biofluid. So one way that allows us to accelerate the test is the hydrolysis reaction. We measure the material change over time in PBS at high temperature, and then we extrapolate back to human body temperature. And we also benchmark with other material like silicon and silicon oxide. The silicon, the material, about 2 or 3 micrometers of silicon was removed after 8 days in PBS. For silicon oxide, about 600 nanometers of silicon oxide was removed after 8 days. Silicon carbide, after 8 days, 90 degrees C, the thickness remained constant. And also, we want to use silicon carbide as a barrier to protect underlying electronic, like transistor for bioamplifier. So we want to see how water and ion diffuse through the silicon carbide and attack the underlying electronic. The way that we test is to use magnesium membrane, because magnesium is highly reactive with water. If you put magnesium in hot water, you see the reaction and the change of the surface by your naked eye. So we deposit magnesium on the outside of silicon carbide, put a reservoir on top, and then observe how water diffuse through the silicon carbide membrane. And before we did this test, we also confirmed that there was no helium leak test. Helium leak, meaning the material or the membrane was pinhole free. And we benchmark with other common material like zinc oxide can only last less than half a day. Silicon nitride maybe a day. Silicon about 2 days. And silicon carbide after nearly 2 months is water diffuse through the membrane and attack magnesium, meaning the material is very good for biobarrier. And we also measure the electrical property stability of silicon carbide in PBS at 96 degrees C. The conductivity of both N-type and P-type remain constant, and its electrochemical impedance spectra also quite stable after 12 days. So it means you can use that as a sensing element, either through the piezoelectric effect for mechanical sensing or thermoelectric effect for temperature sensing, or as an electrode for stimulation and recording. And before we implant into the animal, we need to explore the biocompatibility of the material. And because it's dry bandgap, so it is transparent to visible wavelength. And we can observe cell grow on the membrane, and we confirm that we have quite good cell viability after several days of culture. We also implant the material inside of animal, which is rat in this case, and your bike and leave the rat live for several weeks. And after a week, we reopen the implants area and check the inflammation reaction. So there was no significant inflammation reaction, and the rat reaction was quite normal with and without the membrane, indicating its biocompatibility. And for application, there are several potential applications that we can use with implanted silicon carbide at electrode. For example, one of those is for peripheral neuron stimulation. And this work has been reported by Professor Coachins at EPFL about using peripheral neuron stimulation to regain walking functionality in patients with spinal cord injury. The idea is in patient with spinal cord injury, the brain still sends a signal to the thigh. The muscle of the thigh still function properly, but the problem is the signal from the brain cannot be delivered to the thighs due to the injury. So one way we can read the brain signal, decode the intention of the patient, and then send proper stimulation signal to the targeted muscle to help the patient walk again by themselves. So with the same concept, we tested on animal. The material is highly flexible so that we can wrap around the sciatic nerve of the rat. We can see clear EMG response at sufficiently high stimulation voltage, and we can also control the bending angle of the rat at a demonstration of peripheral nerve stimulation. Another application that I have demonstrated recently is for cardiac defibrillator. Conventional device only stimulate a two position, which require high voltage and can lead to pain and also limit battery life. Another concept to overcome that problem is to have electrode array wrapping around the surface of the heart, and we can simultaneously stimulate several points at the same time. By doing so, you can reduce the stimulation voltage and also can have longer battery lifetime. But the problem is you use electrode for this kind of flexible electrode patch, they cannot last very long because of the reaction. When you apply voltage for stimulation, you actually promote the electrochemical reaction on the electrode side, and they will gradually process. And because our silicon carbide material is chemically inert, and it also have relatively large potential window, so we can use that for simultaneously stimulation of the heart. We make electrode array and wrapping around the heart tissue of a rabbit model, and we confirm that we can paste the heart with our regular bit. And in this application, we still use 2D silicon carbide electrode array, which is good for simultaneous stimulation. But one problem with this kind of application is in some case, you have to implant the device at early stage. For example, for a young kid, and they keep growing, the organ keep growing. However, with this design, the electronic cannot grow. It will have good flexibility, but not stretchability. So to overcome that problem, we come up with a stretchable silicon carbide electronic using the 3D structure, which has been very well developed by Professor John Roger and Yu Chang at Tsinghua University. So we use buckling concept to try to form silicon carbide 3D structure, and we found that this structure can enhance the stretchability of even a very brittle material like silicon carbide, and it can stretch up to 100%. It can deform without any significant change in the electrical conductivity.
Yeah, maybe we should be a little bit faster for the time. Yeah, thank you.
Sure, I will finish my presentation here. So this is the demonstration of our stretchable electronics. And finally, here's the conclusion of my talk. We have a lot of opportunity in silicon carbide for extreme environmental sensing, a long-term barrier, and also growing electrodes for long-term implants. And finally, I would like to thank our collaborator. And we actively looking for PhD student. We have a few PhD scholarship available in my group. So if you're interested in doing PhD in Australia with my group, you are more than welcome to contact me. Thank you.
Yeah, thank you, Professor Fan. Yeah, very nice talk. So we'll keep the Q&A session at the end. So maybe you can stop sharing now, and we'll
Sure.
start. Thank you.
Thank you.
Okay, so we'll have another speaker, Professor Haotian Chen from University of Glasgow. Today's topic is about the stretchable electronics and their application in restoring the human sensory motor system. So Professor Haotian Chen now is a lecturer, the assistant professor in biomedical engineering division at the University of Glasgow. He obtained his PhD in Peking University, and then he conducted the postdoc research at the EPFL, and in 2022, he was appointed as a junior professor in French National Center for Scientific Research, and then he appointed as joined the University of Glasgow in July 2023. His primary research focused on the application of stretchable electronics in different areas, such as the tactile prosthetics, including the wearable electronic devices, nanocomposite, intelligent prosthetics, and teleoperation. He also published over 60 papers in related fields and filed eight domestic and international patents, and served as the editorial board and the reviewer for several journals. He also was recognized with different international academic awards and joined the IEEE I2MTC and some other awards from the UK and the ANR. So let's welcome Professor Chen.
Hello, can you see my screen now?
Yeah, sure, you can go ahead.
All right, thank you, Professor Soames. Wonderful introduction, and thanks for Professor Alice Jones for this opportunity to give a talk and have a discussion with all talented researchers here. So today my topic is about stretchable electronics in restoring the human sensory motor system. I'm from University of Glasgow. The school of this engineering school is called James Watt School of Engineering, to name or to memory the very famous engineer James Watt, who converted the steamer. Yeah, so which means we have a very long history in this engineering study. So my research really focuses on how we feel or we touch to the world. So if we look at our human perception and the target, so for example, you're playing some instrument. So how to interact between our human perception and the target? So there are three main categories from our five senses. The first one is sight from our eye, and hearing from our ear, and also touch from our hand. So the corresponding physical parameter we would like to perceive is light, sound, and the physical texture of this object. So that is how we, as a human, to naturally feel the target. In terms of technology, we need to introduce some technology to convert these kind of technologies. So for the visual information, we use camera to capture the information of the light, and they use a screen to reproduce the light information. And for the hearing or the sound of voice, we use a microphone to record our sound and use a speaker to produce this sound. Okay, so that's a reason why we can use this Zoom meeting or this online meeting to meet each other, to talk to each other. But how about touch? So if we look at technology involved in here, there are from the natural feeling to the physical features, we need at least two technologies. So first one is a record the physical information in the way that we can modulate. So like a camera, we capture this picture, we can use pixel to study it, and we know that brightness and so on. And then another thing is we need to have another technology to regenerate the way that we can, as a human, we can feel it. Okay, so my research or my researching interest really mainly lay on this sense of touch, how to record the sense of touch and how to produce the sense of touch and something related. So if we look at the sense of touch, there are two aspects. So the first one, we call it the cutaneous sensation, which is around our skin surface. It's mainly used to interact with an external object. So when we touch our skin, when we touch our table, we feel the softness, we feel the roughness. The other part is called kinesthetic. It's mainly about how we human know that how our joint is moving. So I'm reaching my hand to a remote, like a cup remotely. I know my joint is moving. So in terms of to discuss the feature of the touch, we need to consider both of them together. So if you look at how we relate our nerve system to the target, there are like from motion part and from sensation part, there are this like closed loop. So first from your brain or from your nerve system, you generate the motion. You want to reach out to a cup remote to you. And then you know like you are how to reach to that object. So that is motion identification. Once you get in touch with the object, your skin will sense the texture of this object. And this sensation will be generated through your nerve system back into your central nerve system. And then it will become this closed loop to move on. However, the tactile or sense of touch is really, really special compared to the hearing or the sight, because there are two main features. The first one is that the tactile sensation is dependent on how we move. So like when we press an object, we mainly feel the softness of this object. But when we slide over the surface of this object, we feel the roughness. So it really depends on how we move and what kind of texture or object feature we can feel. So that's the first feature. It's different from our vision or hearing, like how we move, we don't basically change how we feel. Okay. The second thing is like the process of touch has the potential to physically change the target. So like if I'm touching a foam, which is very soft, how to feel that this foam is soft? We make it deformed, right? We know that comparatively how much deformation happening in the foam and how much deformation happening in our finger. So that's the way that we calculate or we perceive the sense of like the softness. But like our vision by, for example, looking at some light, we won't change the light wavelength or frequency. So that's very, very interesting. So the touch is mainly about the closed loop sensing. So we need to consider the way how we move and how we feel in the together. So that's the reason, like in today's talk, I will cover like the motion and the sense together. So when it comes to like we want to describe our human or features, so very, very beginning, we use this stick or calendar model to describe how we behave. But our human, like human body soft, can the sensor follow the stretching or movement of the human? So that's the reason we need to introduce the stretchable electronics to cover like the new human model. So I think if you are familiar in this the field, you know like there is a balance between the mechanical performance, like the high-end electrical performance material usually come from like a brittle metal or semiconductor. But on the other hand, the rubber or silicon elastomer, they are very stretchable, but they don't usually have this function. So we would like to combine the two features together to achieve this like stretchable electronics and use this stretchable electronics to study the sense of touch. So my research mainly covered the material. We'd like to maybe prepare or develop some new material and based on some structure design and advanced fabrication process, we would like to achieve the soft electronics. Okay, so you will see like I use this diagram to indicate like my research area. So from nerve system to target. First of all, I'd like to first introduce the motion identification and the sensation identification, which is more like the sensor part, like how we capture the feature of sense of touch. Okay. There is another very interesting thing is like from the engineering topic, when we describe these kind of features, we use strain, pressure, vibration, temperature to describe the cutaneous perception, the sense from your skin, and use displacement, velocity, acceleration, and force to describe how you move. But actually, for our if we describe it from our natural sense or psychological way. We don't tell, like when we press, when we use our finger to touch a table, we don't say, okay, I'm using, for example, 10 Newton force to press it. No, we don't talk in that way. Instead, we talk in the way like, okay, this object is soft and the surface is rough. And when I move on it, I feel a lot of friction and warm and cool. So how to translate the engineering term into a more like psychophysical concept? So in terms of like roughness sensing, we need to combine the sliding speed and the vibration happening at our skin to indicate or derive the feature of the roughness. And in terms of softness sensing, we need to also consider the displacement, how we are touching this object, and the pressure we get from our skin and strain from our skin. So it's a combination between the cutaneous perception and the kinesthetic perception. So I will introduce like this motion sensing and this cutaneous perception one by one. So my first part of work is like a liquid metal based strain sensor to monitor the hand motion. So liquid metal is a very ideal material for the stretchable electronics because ideally it's in the liquid state, it's very stretchable and it has quite good conductivity. But in terms of the fabrication, we realize a couple of problems. So the first one is there is an oxide layer around this like liquid metal. So when you want to pattern liquid metal in a very fine structure, it's very, very tricky because the oxide skin will block it's like the liquid to flow naturally. The other feature interesting is like in a non-oxide environment, there is no oxide skin of the liquid metal. The liquid metal become very, very easy to adhere onto this novel metals such as platinum or gold. So it's have this selective wetting property. By using these two features, we introduce this liquid metal fabrication process, which is like on the very soft and stretchable substrate PDMS. We first directly deposit the liquid metal, the gallium-based liquid metal onto this gold, and we can see that, okay, the contact angle is fine in the non-oxide environment. But now we regard the liquid metal as a liquid, totally use the engineering tools to study liquid. So, by providing this small feature or microstructures on the top of the substrate, the wettability can be well modulated. So if we like create these tiny pillars on the PDMS, the liquid metal can homogeneously deposit onto this microstructured PDMS. So in this way, we can make the liquid metal layer very, very smooth. And further on, we can use lithography or the process from the clean room, from the traditional like microelectronic fabrication to pattern it into a very, very high resolution. So with the help of this iron etching, we can achieve like, I'm not sure you can see my mouse on the screen, but you can see the channel here. You can see the channel here. The width of the channel is around 1 micrometer. And that's 1 micrometer channel, 1 micrometer channel, and the gap between these two micrometer channel is 2 micrometer. So in this way, we prove that we are able to fabricate liquid metal in the resolution of 1 micrometer, which is very, very high in liquid metal fabrication. Further on, actually, with the E-beam lithography, and the resolution can be or even improved. Based on this technology, we use this like liquid metal to pattern the strain sensor and put it on the finger. So this is a demonstration like how we use liquid metal to capture the joint movement of the finger to easily compare to the IMU setup to it's more conformable to capture the feature of the movement. Okay, that's how we would like to capture the motion feature. And then I'd like to introduce something about the skin-inspired tactile pressure stuff, like how we feel at our skin. So this is the part of work I have done during my PhD. So I regard this opportunity as a good reunion. So my supervisor, Professor Alice Zhang, and the co-author, you both of them here. I think it's good to recall like my previous work and how this work helped me to develop my current research. So we would like to study from the the feature, the bio feature of this finger. So we would like to introduce like the spiral, the fingerprint inspired electrode to feel the sliding, and the porous carbon nanotube PDMS to sense the pressure. So the way of preparing the material is first to mix the PDMS and the carbon nanotube together with the help of a tolerating. And then according to the ratio of this carbon nanotube, we can achieve different sensitivity of this piezo-resistive material. And in terms of the sensing, sliding sensor, this spiral, like two spiral-shaped electrode, when it come across this surface with a gap in between. So the electrode, or the electronic will go through the two electrode. So there will be some voltage generating by counting the number of this waveform. We can identify the surface of the roughness. So we use the simulation and the real test to prove this idea. And following on, in order to further improve the sensitivity of this pressure sensor, we introduced, based on the carbon nanotube PDMS, we introduced a porous structure, because this porous structure gives us more space, easier to be informed. So we also studied the mechanical model to study why there were two segments of this sensitivity, and how to modulate the sensitivity by changing the ratio of the PDMS at the porous structure. Further on, we also introduced the structure with this hybrid structure, the porous structure plus this pyramid structure. So the pyramid structure can further improve the sensitivity under pressure. So we also study the different shapes, different outer shape, and different porosity to influence the sensitivity in general. I hope this kind of work covers all the solutions to improve the sensitivity of the pressure sensor, because normally when it comes to the pressure sensor, above the material itself, we mainly need to study the structure, and the porous structure and this pyramid structure are the two most popular one, and is already widely being used in a lot of research. So after studying the separate sensors, I'd like to really start something interesting or really related to our life. So interaction between the sensing unit and the object. So this problem comes from when we human touch an object, we can easily feel the softness of our target. But when it comes to the robotics, it doesn't have this ability to feel the softness. Why is it important to detect or study the softness detection? Because just imagine a case, the pressure sensor is made of soft material. And when we test it on the standard platform, the pressure sensor gets compressed. But when we use this soft pressure sensor onto a soft substrate like our human body, under the same pressure, because our human body is also soft, both of this part, the sensor and the substrate, will be deformed. So the readout of the sensor can be changed. So that is how we analyze how the sensing unit the softness, the softer or rigid, and the target, how they interact with each other. So the very tricky one is in the soft sensor unit and the soft target, because the deformation will happen on both parts. So to solve this problem, we introduce these new structures to include the pressure sensor and the strength sensor together. Above the strength sensor, there is an air space here. So when we use this sensor system to contact the rigid target, the pressure sensor, so there is no or very little deformation at the strength sensor. So the ratio of the strength sensor and the pressure sensor is very low. But when we use the same structure on the soft target, the strength sensor will deform much easier than the pressure sensor. So if we compare the ratio between the strength sensor and the pressure sensor, so the ratio is high. With this feature, we are able to identify this, like the softness of the object. So here we use liquid metal to fabricate the strength sensor and pressure sensor in one platform. So I will go quicker because we are running slower. So here is the simulation, how to choose the purple materials under the same external pressure. We would like to study the sensor material and the target material. So I just quickly show the result and some interesting conclusions here. So for the sensor material, no matter what target it is, the softer sensor always bring more deformation. So we need to use softer material to fabricate the whole sensor. But when it comes to the target material, in the strength sensor, the softer target can cause more deformation. But in the pressure sensor, the harder target will cause more stress, which means for a given target material, the strength sensor and the pressure sensor, they behave different or opposite trait. So that means the target's elasticity can influence the readout of the sensor. So furthermore, I also introduced some mechanical model to study this, and this is a picture to show how our system can identify the sensitivity of this softness. So I just also go quickly about today's conclusion. So for the strength sensor, the harder sensor material can have high sensitivity to identify harder target, and softer material has high sensitivity to identify softer target. Okay, I can use one sentence to summarize our discovery and our conclusion from this mechanical model. Just imagine we are using our finger to identify, to touch the wood and to touch the iron or steels. Although the wood is much softer than the steels, from our finger, we cannot tell it because our finger is too soft. But when we use our finger to touch elasticity, like the silicon or the jelly, well, we can easily tell the difference because our finger is soft. We are good at distinguish the softer materials. So our model can explain it, and which is exactly the same scenario in our real sensation. Okay, so based on some equations, some calculation, we're able to identify the softness of the different material like hydrogel, EcoFlex, PDMS, or some commercial rubber, and we use this sensing system to equip it on the robotic hand so that the robot can feel this pressure and compliance of the object by pressing it. So after we get this sensation identification, we want to also generate some sensation, just like we are talking. I hope in one room, the robot can feel the softness, and in the other room, the human, the operator, can feel the haptic feedback. So in order to achieve this, we introduce this pneumatic actuator. It includes two parts. The first part, the top part, it can deformed to mimic the deformation of the surface. The bottom part is to detect or change the displacement along this vertical displacement. So this is how it works. So there are two main areas. The contact area will be driven by the pneumatic actuator. The bottom part is also, but it's mainly to render the displacements change. And we considered different type of object, like this is a material made of fully soft material, and for the other case, maybe some have the stiffer skin but softer below. So we first use the sensor to record the sensor feature, and then we use this actuator to generate the sense of touch. Further on, we also hope to use this tactile sensor to equip with the exoskeleton so that the exoskeleton can have some tactile feedback. So this is also a application. Like we traditionally, the exoskeleton hand can only close and open their hand, but there is no clue of this touch. So we would like to introduce the softness sensor into this system so that the user, when they use this exoskeleton or this robotic hand, when they touch different object, different shape, they can give the better feedback so that the machine can control it in a nice way. And further, the last one is about how we use our stretchable electronics for some implantable applications or some spinal cord injury to some animal or even people. We lose the control of our urinary system. So we hope that we use a strength sensor to feel the bladder state, to feel this expansion rate, and use the spinal cord stimulation to control the spinature, to control the muscle. So especially for the bladder volume detection, we have to use liquid metal analytical flex to fabricate this strength sensor. You can see that the whole device can be stretched to 3 times of its original length without breaking at all. So as a demonstration, so this is one, like we compare our strength sensor with the implantable pressure sensor, with the commercial one, which can capture the feature very well. And the other one is we apply the spinal cord like electrical stimulation so that the muscle is contracting to take out the urinary liquid. So as a conclusion, so my main focus is around the motion, the sense of touch, including motion generation, motion identification, sensor identification, sensor generation. The basis is I always look for the new material structure to fabricate cool devices, and also I hope to work together with multidisciplinary computer science, virtual reality, robotics, and bioneuroscience. All right. Thank you very much for your attention.
Okay, yeah, thank you, Professor Chen, for your nice talk. So let's move to our next session. So maybe all the speakers could turn on your camera and also unmute. So we'll have 2 professors as the panelists. So first is Professor Yanfang Guang from Henan University of Technology, and another is Professor Haixia Zhang from Peking University. So next we'll have a panel discussion, so everyone can post any questions or anything you want to discuss.
Okay. Hi, maybe I go first. Hi, Yanfang. Yeah, I go first. Okay. Yeah. Exciting to hear you talk about silicon carbide MEMS. Actually, that's a long time ago. Yeah, I also work with silicon carbide. Yeah, so about I hope you can give me some details for how in your process to get the pinhole off. If you use PECVD or LPCVD to grow deposit the silicon carbide, they'll always get some pinhole. The material is not that kind of perfect. Yeah, so you use the high temperature annealing or any other process to make it? Hi, Pang, can you respond? Oh, no. Yeah. Hi, Yu, can you hear me?
Yeah. Yes, I agree with you. That's
Please.
yes.
Yeah, Professor Fan, you
Yes,
can
can you
go
hear me
ahead.
now?
Yeah, we can
Yes.
hear you. You can go ahead.
Yes. Yes. So yeah, thank you very much for your question. And I think the grow process is very critical to create pinhole-free thin film. The PECVD normally make amorphous material. Like it also happened in silicon nitride when they grow silicon nitride using PECVD. You have a pinhole because you have multiple flakes lying on top of each other. Then pinhole will form between the junction, the interface between the layer. But here we use a low pressure chemical vapor deposition process. So we epitaxially grow silicon carbide on silicon. The first step, we carbonize the silicon substrate. And after that, we put layer by layer of silicon and carbon on top of each other. So by doing epitaxial grow, we have the crystal silicon carbide, but not amorphous silicon carbide. And the crystal silicon carbide that have multiple flake, that like the case of amorphous, that avoid forming the pinhole between the flake and flake. However, if you grow very thin silicon carbide membrane, when the film is not thick enough, it still have some defect, and the pinhole can be formed between high density defect layer, which is about 40 nanometer at the bottom. So to get rid of the defect of the pinhole, you have to grow it a bit thick, like about 100 nanometer. The film will be pinhole free, but below 40 nanometer or so, you may still have some pinhole in the film.
Okay, I see. Thank you very much. Yeah. Hi, Yanfang. Maybe you can go ahead to ask.
Yeah. Hi, Professor Pan. Yeah. There are lots of usage for the silicon substrate, such as the ocean, energy industry, mining industry, gas, leakage, and space. So maybe there are some difference between these usage for the silicon carbide. So maybe you can, would you like to explain? Hi, Professor Fan.
Hello, Professor Fan.
Yes, I think my internet connection is not very stable now. Maybe it's quite late and the internet a bit tired. I think, can you please repeat the question again? I got the first part of the question, but the second part, I think the internet wasn't very stable.
Okay.
So the first part you mentioned about application in space and deep sea exploration, right?
No, yes, the usage for the silicon carbide. I mean, for this, lots of kinds usage, ocean, space, and gas, leakage, and so on. Maybe I think the silicon carbide are different. The types of silicon carbide are different, right?
Different from you mean what are the material using for ozone at the moment?
Yeah.
We are, I think, we haven't explored the application of silicon carbide for ozone exploration, but one of our collaborators at Technical University of Delft also working on that area. One advantage of silicon carbide for ozone application is its chemical inertness, so that it can withstand the salty water, and also for Arctic Ocean, where the temperature can be very low, the material can also withstand cryogenic temperature. So it is highly relevant for ocean monitoring application.
Hey, so maybe,
correctly?
Yeah. Okay, maybe how I can give a few comments on this. Yeah. Actually, Yanfang's question is for the silicon carbide used for the ocean or for the of the space. There are really a lot of kind of silicon carbide devices, right? Electronics.
Yeah.
But this, like Han this time he was present about the thin film silicon carbide is used for it's a thin film. So all other the devices made by silicon carbide, it's a wafer is silicon carbide. So that's a little bit different, for the electronics and
Right.
this. Yeah, silicon carbide MEMS. Yeah.
Exactly. So I think we have a bulk silicon carbide and then thin film silicon carbide. So the bulk silicon carbide normally in the form of like 4H silicon carbide or 6H silicon carbide with a hexagonal structure. They can be grow very thick and can withstand very high pressure. However, because they're so thick, it is very hard to make microstructure like MEMS device out of 4H or 6H. The advantage of the thin film is you can make microstructure using standard fabrication of silicon. However, if you want to use for deep sea and space exploration, where the device need to withstand very high pressure level, I think you have to make the membrane very tiny, because the thinner membrane, the more fragile it will be when subjected to high pressure. In that case, to make, for example, pressure sensor using the thin film, you also need to make the membrane really small using maybe e-beam lithography.
Okay, understand.
Okay. Yeah, any more questions?
Hao Tian, yeah. So glad to see you move on, from sensor MEMS sensors and to, can especially if on the target you want to, mimic, right? Yeah, the soft or the hard or this part. So what kind of application you really shooting for? Is it robots or any, other applications?
Yeah, it's mainly so from the sensor itself, it's mainly about the robotics. So we worked a lot with not only the pure robotics, we are more interested in the like exoskeleton. So for example, the patient with the stroke, they need this they have their limbs or the prosthetics, they have their limbs well, but they cannot control it very well. So they need an exoskeleton to help them move their finger, for example, or move their arm. But currently, this like prosthetics or exoskeleton, they mainly can only to control it. Okay, up, open and close. They don't give any feedback. So that's it. The one feature, like we want to replace first, like the human who don't have this natural tactile, but also give like a complementary for the prosthetics or the exoskeleton. That's purely for the sensor aspect. For the actuator part is also very interesting. The actuator part, we have two currently ongoing applications. So one is we would like to connect this with some neuroscience. So like, because when we talk about how we generate the sense of touch, it's very, very hard to evaluate if it is real or it is natural. So we would like to give the feedback, for example, from the skin and study their EEG, the brain signal to compare. So like I'm touching a ball or touching a table and how their response in their EEG will be different. That's the first application. The second one is we are working with like the virtual reality. They are training the young surgeon to practice their surgery. So to practice their surgery, instead of going to the real ones, they use some tools to practice. But if they don't have this haptic feedback, they don't feel, okay, I'm cutting the skin, I'm cutting the fat, I'm cutting the muscle. So we would like to give some feedback to them to train. So that's it. The main part, the two part, like first part is sensor and the other part is tactile feedback. Yeah.
Okay, this is beyond the AR or VR, right? It can get some real feedback.
It's a little bit beyond current VR or AR because currently we mainly use a goggle to watch, to see and hear, right? We don't have enough way to give this sense of touch. So I'm working with this VR team like they are holding a pen, for example, but I gave some other sensor or actuator around this pen, so make the pen can interact with this virtual reality environment, so make it smarter and give some feedback to the human.
Yeah, also follow Professor Zhang's question. I know you always want to differentiate the strain sensor and the pressure sensor. So after you can differentiate, what's next? Like, is there any specific application like required to, the force from different axes or different directions?
That's very important because, if we really look at the autonomics feature of our finger, actually, the micro receptor around the finger, they mainly detect still like strain and pressure. So my aim is first to miniaturize all the sensors, to make it array. The second thing, we need to really introduce the machine learning algorithm to generate the form, because like like for the pixel, for like imaging, like there are a lot of pixels. A lot of pixel can form the algorithm because they have a lot of data. But now for the tactile sensor, they don't form this large scale. So my method first one is introduce a new sensing like mechanism is called the electrical impedance, like macro tomography. So based on the electrode, we can generate the pressure distribution across the surface. And then we want to introduce some new sensors to make like this within like a finger tip size. We would like to add around 200 pixels, so that at least we can collect as much information as possible to generate more data. And also, for what I'm talking about, like for the psychological feeling, we have the softness and also the roughness and the friction. Actually, for the roughness is fine, but the friction is very, very tricky, because like if touching a sticky material, the sticky material will capture your finger, so we will feel something. So you really need to establish a model combining both the tactile cue and how you move. You move faster, you feel different. You move slowly, you feel differently. So we need to really integrate all this possible like a sensing data together to form this closed loop sensing. Yeah.
Okay. Hi, Yu. Maybe I really want to ask these questions. Yeah, not only for Hao Tian. Actually, Hao Tian just mentioned a very good point. Like friction, you have the sensors, the feelings, right? The sensing part, the feelings. So now talk about that. You need if you want to get like the feelings, this not only can tell by the sensor, right? If I use pressure or many sensors, you must mix the the signal, right? You must use machine learning or AI, this kind of technology to enhance or to analysis, right? To give it. So how did you think, AI can help you in this, in this direction? Yeah.
Oh, okay. Like how AI. So first of all, like so there is it's a new topic I didn't put in the slides. So actually, you can use 8 electrode or like several electrodes. Like if I want to map the structure, for example, the area around my palm, I just use the electrode around here, and we don't need the pixel like a row and a column. We just use a couple of electrodes around here. So with that method, in theory, it can generate the full mapping of this surface, but it's rely on the deep learning. We need to use the CNN algorithm to generate this tomography. It's like when we analyze a CT or every like algorithm, we want to identify any algorithm. The picture, like to tell whether this is a dog, this is a cat. So similar algorithm can be applied for the tactile sensor. But a lot of quite something like we need to adjust, because for the pixel, usually it's just that one pixel indicates either red, blue, or green. But in the tactile one pixel means it's an analog signal. So we need to adjust some established machine learning with the physical feature. It's called PIN, the physical informed neural network, to combine the physical sensor and the mapping structure together.
Okay, that will be very interesting. Thank you.
Thank you.
Okay, so due to the time limit,
I also have a question for Hao Tian about your strain sensor for bladder. So that is for implant application. So how is the biocompatibility of the liquid metal?
Yeah, and, thank you for the question. Yeah.
Yeah, and then I think for implants, we want to use that for relatively long period of time. So how have you investigated the long-term performance of liquid metal strain sensor?
Thank you very much. I just want to mention, we're also collaborating with Gegra Kunting, your citing, because their lab is just above our lab when I was in EPFL. Yeah, we're actually working with them. And for the liquid metal, it's not long-term biocompatible, because liquid metal is very active. It's get oxide very, very easily inside the body. But that work is mainly for the acute application. So at that application, we mainly want to study how to stimulate the spinal cord to control actually two parts of the bladder muscles. But in the end, we won't use liquid metal. Instead, we will use gold-based strain sensor. So instead of using the strain sensor cover all around this bladder, we will use the small part, which can only be stretched a little bit, but we can establish a model to predict how much the strain across the whole surface. We probably will use two gold-based strain sensor. One is just imagine it's the volume of this bladder. So maybe one is around here, the other one is the maximum part. By detecting these two strain, we can somehow calculate the volume of this whole bladder. Yeah, so we mainly use gold because we think gold is long-term and biocompatible. But liquid metal is just for a prototype. Yeah. Yeah, but it's okay for, I think, 3 days. 1 week is tricky to see, but yeah.
Yeah. Thank you.
Thank you.
Okay, so if no more questions, so let's thank two speakers and two panelists today. And we also here have a certificate. So first for Professor Fan from University of New South Wales for his nice talk, the silicon carbide nanomembranes for sensing applications. And another certificate is for Professor Hao Tianchen from University of Glasgow for his talk, the stretchable electronics and their applications in restoring the human sensory-motor system. And also for our next Tuesday youth talk, we'll have Professor Wang Haozhang from Tsinghua University Shenzhen as the moderator, and also have several young investigators will join together, and their topic will be liquid metal intelligent materials. So if you are interested, so see you next Tuesday at the same time for the youth talks. Yeah, thank you very much. See you next time.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的。